Morning, everybody. Today we're going to talk about graphs of functions. So the graph of a function f is the collection of ordered pairs f of x such that x is in the domain of f and x is the directed distance from the y-axis and f of x is the directed distance from the f-axis. So from the x-axis. So what this means is, I think I said this wrong, x is the directed distance from the y-axis. So x is just your distance away this direction, or it could be this direction if it's negative, and f of x is the direction either up or down. Okay? So, finding the domain and range of a function. So use the graph of function f to find the domain, the range, and then find f of -1 and f of 2. Okay, so the domain is simply the numbers along the x-axis where there is an answer. Okay, so if we look at this graph carefully, this was meant to have an arrow on the end here. Oops, should have read. Okay, so what happens in this graph? This graph comes from -infinity, it comes up like this, and it turns around, and then it stops right here. Okay, where there's a hole in the graph right there, and it just ends. So, what x's can I put into this? That's the domain. So the domain, which is written like this, with a double bar D, is the set of all x's. Now in this case, I can have any negative number, because this implies that this continues down forever, up to, but not including 4. So we're going to say the domain is the set of all x's where x is less than 4. Okay? So it can't be 4 because there's an open circle here. Can't be anything bigger than 4, there's nothing else out there. So that's the domain. Remember, domain is along the x-axis. Okay, where does this equation have an answer? Now the range is everywhere there's an answer along the y-axis. So if you look here, this goes to -infinity down here. So this goes all the way down here like that, but it comes up and it stops right here. Let's make this a little bit brighter of a color here. There we go. So then the range, which we write as a double barred R, is the set of all y's where y is less than or equal to 4 in this case, because 4 is included, because the 0.24 is right there. Now this is a coincidence that these two came out to be the same thing. You can also write things like, if let's say the domain was, could be any number, okay? You write that like this: the domain is the set of all numbers, x. That's it, you're done. You could write all real numbers, you could write this. But mathematicians tend to be lazy and they like to write things with the least amount of work. And so this is the same thing as that. Okay, so find the domain and range of the square root of x minus 4. Okay, so let's think about what that is. The square root, now one of the ways you can do this is to just do a quick sketch. Okay, so the square root of x would look like this. But then x minus 4, this transforms it, right? And it's inside the function, so it's going to move this function 4 to the, 4 to the right. Really easy to get that backwards because people think negative and they go to the left, right? So there you go. I can't put a 3 in here because that would square root a negative number then. So now, can I write the domain and range from the picture? Yep, I sure can. So the domain is going to be all the x's where x is greater than or equal to 4. 4 seems to be coming up a lot with this today. Now the range, let's see, I'm going to get all the positive numbers because this is going to get as big as I want, although it takes a long time to get big. I'm also going to get all the negative numbers that I want because my answers are going to be plus or minus. I'm also going to get 0 right here. So the domain is the set of all real numbers. Why? Okay, the vertical line test. This is really important and very easy. A relation is a function if and only if there is no vertical line that will pass through more than one point on the graph. So which of the following graphs are functions? All right, so what I need is I need a vertical line. Let's make it a nice bright color like this. So if I have a vertical line right here on each one of these graphs. Okay. Now on this one, if I take this and I'm able to move this vertical line this way, you'll notice that it only passes through the graph at one point each time. Okay, so since it does that, this is a function. So we would label this a function. Now over here, this one, whoops, there we go. If I move this right there, it crosses the graph at 2 points. Once here and once here. So this is not a function. Fails the vertical line test. Okay, we go down here and we take this on this cubic right here, and you know what? Excuse me. It always only passes through 1 point. So again, this one is a function. And then this one here, obviously, that fails right there. And you only have to fail once. So this is not a function. Circles are not functions. Okay, increasing and decreasing functions. So a function f is increasing on an interval when if for any x, x1 and x2 in the interval, x1 is less than x2 implies that f of x1 is less than f of x2. All right, if I do a graph of something that that makes this really obvious. So an increasing function obviously looks like this, okay? And here I have an x1, and here I have an x2. And x1 is less than x2 here. Here's my f of x1, and here's my f of x2. And notice x1 is less than x2, f of x1 is less than f of x2. Okay, and it doesn't matter where I move the, oops, I can't, there we go. Uh-oh. There we go. Doesn't matter where I move this, as long as it's less than x1, x2, my f of x1, let's ungroup this. Okay, so if I move my x1 over here, then my f of x1 is here, and it's still less than f of x2. And that will always be true. So let's look at a decreasing function. Well, that's just going to be the opposite. So a decreasing function, function f is decreasing on an interval when for any x1 and x2 in the interval, if x1 being less than x2 implies that f of x1 is greater than f of x2. So that would be a situation like this. So I would have an x1 here, and I would have an x2 here. And then decreasing function would look something like this. Okay, and my f of x1 would be here. And then my f of x2 would be here. So x1 is less than x2, but f of x1 is bigger than f of x2. And as long as x1, whoops, as long as x1 is less than f of x2, it doesn't matter where it is, f of x1 will still be bigger than f of x2. Okay, so a function f is constant on an interval when for any x1 and x2 in the interval f of x1 is equal to f of x2. So we can draw that as well. Okay, a constant function looks like this. It's a horizontal line. Okay, and here's x1. Here's x2. It doesn't really matter where they are on the graph. I can mix them up, put them anywhere they want. But f of x1 is equal to f of x2. So it doesn't matter where I slide this. This will always stay on that line and always be equal. Okay, determine the open intervals upon which each function is increasing, decreasing, or constant. All right, so let's look at this f of x equals x cubed right here. What is the interval on which it is increasing, decreasing, or constant? So it actually looks like this. Okay, so what's happening? Well, this is getting bigger and bigger and bigger, and then it kind of slows down, it evens off, and then it starts getting bigger and bigger and bigger again. So this is increasing everywhere. Now we're going to write an interval notation, okay, which looks like a point, so you got to know context. But the interval notation that this is, we would say this is increasing on negative infinity to positive infinity. And that's along the, we're considering along the x-axis here. Doesn't matter where I am, this is always getting bigger and bigger and bigger. Now this one's a little more complicated. Okay, so this one is, this one's increasing right to here, and then it starts to decrease again. So what's this point? Well, this is the point, this is -1 right here. Okay, and this is going to be, no matter how far I go to negative infinity here, this thing is always getting bigger and bigger and bigger. So we say it's increasing from negative infinity to -1. Okay? That's not a point, that's an interval. Now, it's also increasing from here to infinity, okay? Because it's down here and it's getting bigger and bigger and bigger this whole time. So we say union 1 to infinity. So there's two intervals where this thing is increasing, from negative infinity to -1 and from 1 to infinity. And this little U sign right here is a union. It means to put those two things together. Now it's decreasing from -1 to +1. And again, I can't emphasize enough, you need to understand context. That's not the point -1, 1. And you don't say it's decreasing from 2 to -2, because you're talking intervals on the x-axis. Okay, let's look at this one. So this function is increasing here, then it's constant, then it's decreasing. So we would say this is increasing on the interval negative infinity to 0. So it's increasing here. This is constant from 0 to 2. It's constant right here. And then it's decreasing from 2 to infinity. So it's let's do this. It's decreasing, whoops, from here to here. Let's kind of change this up so it stands out just a little bit. Okay. Relative minimums and relative maximum values. So a function value f of a is called a relative minimum of f when there exists an interval x1, x2 that contains a such that x1 is less than x is less than x2 implies that f of a is less than f of x. Okay, that's a lot of mathematical terms right there. What does it mean? It just means this. If you've got some interval, so in this case, I have an interval that goes from actually negative infinity to anywhere, like clear up to 1. So this interval here to here, this is the biggest value in there. Okay? So that's called a relative maximum because this is the biggest value on the interval negative infinity to 1. Okay? Now, this is a relative minimum because it's the smallest value between, say, negative 1 and positive infinity. So this would be a relative minimum right here. Basically, it's peaks and valleys. Do I have a peak? And you can have lots of relative maximums. You can have lots of relative minimums. You might not have any. Okay, now what's the difference between a relative maximum and a maximum? Well, this function has a relative maximum right here because it has a peak and then it comes back down. Okay, so that's the biggest point here. But it does not have a maximum because this thing goes to infinity. Okay, so it goes like this and it takes off and it keeps getting bigger and bigger and bigger. Now you can have a relative maximum and a maximum. You could have a graph like this. Okay, so this function right here has two relative maxes. There's one right here, and there's one right here. This one is a relative max. This one is just a maximum. Okay, that's as big as it gets. This one doesn't have a maximum because the arrow implies it goes to infinity. It also has a relative minimum right here. Okay, but it doesn't have a minimum because these arrows imply that it goes down to negative infinity. Okay. Could you have a maximum and a minimum, or a relative? Yeah, could you have a maximum and a minimum? You could have some kind of funky things that, I don't know, look like this. Okay, so this has a maximum right here. This has a minimum right here. And then they approach 0 on either end, so okay. Approximating a relative minimum. So use a graphing calculator to approximate the relative minimum of the function. Okay, so how do you use your graphing calculator to do this? So the first thing you want to do is get out your handy dandy TI-84 plus C Silver Edition graphing calculator. push the y equals, make sure there's no equations that somebody else has left in there, and if there is, clear them out. And then in y1, we're going to go ahead and put 3x. Now your x key is right next to your green alpha key. So 3x squared minus 4x minus 2. We're going to put that in the first equation and hit enter. Okay, we'll go to our window. And we're just going to go ahead and have a window from negative 10 to 10. So the x min would be negative 10, the x max would be 10, the x scale will leave 1, the y min will make negative 10, the y max will make positive 10, and the y scale will leave 1. And the x resolution, we'll just leave it, we don't touch that. So that's probably the window that's already in there, but sometimes people change those, so be careful. So we'll hit graph, which is in the upper right-hand corner, and we get something that looks like this. Pretty tall, narrow graph that kind of goes like this. Okay, now you can tell from the graph, this is a parabola, so it's going to be, and it's open up, so it's going to have a minimum, okay, and the minimum is going to be right there. All right, so, but it's hard to tell where it is on the graph, so here's what I'm going to do. If you look along your top 5 keys here, the fourth one says calc above it, so hit second, the blue key, calc, and then you'll see number 3 is a minimum, so just hit 3. And what it does is it puts a little X on my graph, and it put mine right about there. Okay, and I'm going to use the left and right arrow keys. I'm going to use the right arrow key, and I'm going to move it. If you look here, it says left bound at the bottom. So what they're going to do is they're going to ask you for a left bound and a right bound, and then it's going to guess the lowest place between those two. So this would be a left bound right here. I can just hit enter. I usually try to be fairly close to this. And now I'm going to use my right arrow key, and I'm going to move this arrow, or this X, so that it's over here on this side of the minimum. And notice it says right bound now on the bottom, so hit enter again. And you can also see that it puts these little triangles kind of like right here, like this. And what it's going to do is it's going to find the smallest place between those 2 points, okay? And then it says guess, and go ahead and hit enter again, and it tells me x equals 0.66666488, and then it says y equals negative 3.33333. Okay, so what does that mean? Basically, that means this could be a rounding error. I'll bet you this is just 0.666 repeating. So the x would be 2/3, and the y would be negative 3 1/3, which usually at this level of math we would write as negative 10/3. Don't use mixed numbers very much. Okay, so there I found my minimum. And if you go back and you look at calc, push your calc key again, second calc, sorry. You can also find zeros this way. You can find maximums this way. You can find intersections this way. During a 24-hour period, the temperature, Y, in degrees Fahrenheit of Milwaukee, Oregon, can be modeled by the following formula. Y equals 0.026x cubed minus 1.03x squared plus 10.2x plus 34, where 0 is less than or equal to x is less than or equal to 24. Where x represents the time of day and x equals 0 corresponds to 6 a.m. Approximate the maximum temperature during this 24-hour period. Okay, this is an equation you're going to want to use a graphing calculator to find. Okay, so we're going to go back to y equals. We're going to clear that equation. We're going to type this one in its place. 0.026 x to the third power. Make sure you arrow down from your power. Minus 1.03 x squared plus 10.2 x plus 34. Okay, and then we're going to go to our window, and we want our x's to go from 0 as our minimum to 24 as our maximum. And we'll count by ones. I think we'll be okay with that. Might have to count by twos, but we'll try it with ones. Now, what do we want our y's to be? Well, what's a reasonable temperature? You know, it could go as low as like -10. So we could make the minimum, we could leave the minimum -10 here. And it could maybe get up to 105 degrees. So we'll put 105 in there. And we'll count by, I don't know, 5s. Okay, and we'll go ahead and hit graph. Okay, and if you look at your graph, it kind of goes like this. Okay, so the maximum temperature appears to be like right about there. So what we're going to do, we're going to go second calc. 4 is going to be the maximum. Now I put my x right here, and it's asking me for left bound, so I need to move my x clear over to here somewhere. So I'm going to use my left arrow. I'm going to make sure I'm past that peak. Okay, so I hit enter. Now it says right bound. So now I'm going to move it so that it's on the right side of that peak. So I arrow to the right, and I hit enter, and now it says guess, and then I have a guess, and it says x equals 6.6 and y equals 63.9. Okay, so what does that mean? Well, this is hour 6.6. So remember that 0 is 6 a.m. So this is 6 a.m. right here. So this would be 6.5 hours, a little over 6.5 hours later. This is like 12:30-ish, or about 12:45-ish. Okay, and it's going to hit about 64 degrees. Okay, now if we wanted to know what the minimum temperature was going to be, that is hard to tell on this graph. It could be here, or it could be here. So we could plug 0 into this really easily, because if I plug 0, this is gone, this is gone, this is gone. It's just 34. So I know that this is 34 degrees right here. So then I can go look at this time over here. So, and I can calculate a minimum. So let's do the second calc. This time we're going to do a minimum. And I'm going to move my arrow to the right till it's about here. Hit enter. Then I'm going to move it more to the right until it's over here. And I hit enter again. This is guess. And it gives me x equals 19.8. And y is 33.98. So it's like, yeah, 33.98. Okay, so what does that mean? Well, this would be the overall minimum right here. This is slightly less than that. It's pretty close. I mean, if you round it, you would say, okay, the minimum is 34 degrees. What time is that? 19.8 hours. Well, let's see. If 6 a.m. is 0, then 6 p.m. would be 12. And so then 7.5 hours after that. So let's see. That would be 6. Another 6 would be midnight. 7 would be 1 o'clock. So this is about 2 a.m. Okay, and you're going to have so you have two minimums here. You have two relative minimums for sure. You have a relative minimum here at 34. You have a minimum at 33.98, which is probably just really 34. So you can say it has a minimum at 34, but it has two relative minimums, one here and one here, because they each have their own interval. Okay, step functions and piecewise functions. So the greatest integer function, which is kind of written like this sometimes, and defined by the greatest integer less than or equal to x. So what that means is if I take the greatest integer function and I have the number 3.5, then the greatest integer less than that would be 3. Remember, your integers are -3, -2, -1, 0, 1, 2, 3, and so on, right? So it's always less. Now the confusing thing, people don't usually have trouble over here, you know. If I say, oh, what's the greatest integer of 4.9, they'd say 4. Okay, the greatest integer of 1.2, it's 1. Greatest integer of 0.6, it's 0. Where people have a problem is the greatest integer of -1.5. Well, -1.5, the greatest integer less than that would be -2. Because they think of the absolute value, you think of this as getting bigger over here, but it doesn't. It's getting smaller. Okay, so the greatest integer of -2.1 would be -3. And this is why it's called a step function, because it looks like stairs. Okay, so what happens is this from 0, your greatest integer is 0, and then it stays 0 until you reach 1, and then it has an open circle and it jumps up to here, and then it's 1 until it gets to, you know, all the way 1.9999999. As soon as it hits 2, it jumps up to the next one. Boom. So notice you have closed dots on the left side because that number is included in this, and open circles on the right side because that number is not. 2 is not an answer in here, it's up here. Okay, what's the domain? Well, the domain is easy. The domain is all real numbers. I can take the greatest integer function of any number. What's the range? Okay, the range is interesting because there's no decimals in the range. If you look this way, if you're looking at numbers this way, there's nothing in between 0 and 1. So the range is the set of all y's where y is an integer. Okay, the x-intercepts. This has an infinite number of x-intercepts. The x-intercepts would be, how could I write this? I could write this as x where 0 is less than or equal to x is less than 1, comma 0. There's my x-intercepts. So anything where x is 0 or less than 1 works. The y-intercept is just the point 0, 0. It's just right here. Okay, describe the function. The function, let's see. The function, and this is where people are not very good because lots of people that are really good at math are not good at writing out what that means. Okay, so the function, to describe the function is a series of horizontal segments on the integers okay, so I'm on -4, and then it gaps up to -3, and then it gaps up to -2, and so on and so forth. And these are all horizontal segments. We could say it's inclusive on the left side, meaning that this is an answer for this one, but not inclusive on the right side. Meaning there's an open circle on this end. That's not included. Okay, piecewise functions. So piecewise functions are just functions that have different parts to them. Okay, so this tells me f of x is going to be this, which is just a line, but it's only between -1 and +1. It's the number 2 at x equals 1, and it's x squared, which is a parabola, when x is greater than 1. So what does this look like? Okay, so x minus 1. If I was going to draw x minus 1, that's a line with a slope of -1 and a y-intercept of 1. So if I was just going to draw a line, it would look like this. It would have look just like that. That's a little bit skinny. We're going to make it a little wider so you can see it better. There you go. Okay. So there's that line. Now here's the only thing. I only want this line between those 2 points. -1, it's going to be equal to -1, but less than 1. So here's what I'm going to do is I'm going to go put a solid dot right here. And I'm going to have an open circle right here. I just want this part in between. Now what I'm going to do is I'm going to make this line go away. Oh, I just want that part right there. Now, it's 2 if x equals 1. So then this part right here, if x equals 1, the answer is 2. Boom, right there. Then it's x squared if x is bigger than 1. So what does x squared look like? X squared is just a parabola, okay? So 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, -1 squared is 1, -2 squared is 4, -3 squared is 9. So this parabola looks like this. I kind of missed there on that side, but you get it. Okay, now here's the thing. I only want this when x is greater than 1. So what that means is I don't want any of this. I don't want any of this. I got an open circle right here. And then it goes up like this. That's better. Okay. So there's my graph right there. So anyway, that's a weird looking graph, isn't it? So then it says find f of 0. Okay, so f of 0, that's going to fall in here. So f of 0 is going to be 0 plus 1, which is 1. Which makes sense, that's on my graph. 0, 1 is right there. Okay, f of 1, that falls in this part right here. That's just 2. Because it tells me x is, or y is 2 if x is 1. And then f of 2, that falls in this because it's greater than 1. So that's 2 squared is 4. Okay, determine the domain. All right, where does this thing have an answer? Well, it has an answer from -1 to infinity, because this just takes off and gets greater than, right? So the domain the domain of this is going to be the set of all x's where x is greater than, can I be equal to? Yep, or equal to -1. Now, what's the range? Okay, well, I got to find the bottom, the lowest point. The lowest point doesn't quite get to 0. It gets as close as I want to 0, but it never gets to 0. And then it goes as high as I want. And it actually overlaps in some places, but I don't care about that. So the range is going to be the set of all y's where y is greater than 0. Okay, even or odd functions. A function is even if for every number x in its domain, the number negative x is also in the domain, and f of negative x equals f of positive x. Okay, what does that really mean? It means a function is even if and only if its graph is symmetric to the y-axis. So let's look at a picture. So let's look at a parabola, because parabolas tend to be even. All right, here's a nice parabola. It's symmetric to the y-axis right here. So this part right here, what does it mean? Well, if I go out here to x, here's x, and here's f of x, right? And if I go to negative f of x, that would be right here. Well, I get f of x again. Okay, so f of negative x, whoops, this should be written like this. F of negative x right here. So these two are the same value, so you can see f of negative x is equal to f of positive x. And if I move, my x closer to the y-axis, well, then the negative x also moves closer to the y-axis, and this would move inward, and this would move inward at the same rate, so they're always going to be the same. Now, an odd function, a function is odd if for every number x in its domain, the number negative x is also in the domain, and f of negative x equals negative f of x. So a function is odd if and only its graph is symmetric to the origin. What does that look like? Well, let's look at something like an x cubed. Okay, here's an x cubed. So this, if I go out here to x, okay, here's f of x, okay, and then if I take the negative of that, that's going to be down here. This would be negative f of x down here, right? Okay, this is going to be the same distance as here. Now, f of negative x, so that means I go over here to negative x, and I take f of negative x. Well, that's just, well, my graph isn't very symmetric, I guess. Let's redraw it a little bit. Oops, that's blue. That's a little better. Okay, f of negative x is down here. Now you can see f of negative x is equal to negative f of x. Now what is that? Another way to write that or say that is that this thing is symmetric to the origin, which of course is right here, 0, 0. And what that means is if I take this function right here and I rotate it 180 degrees, I get exactly the same function. You can't tell the difference. Okay? All right, so determine whether each graph is even, odd, or neither. All right, so this one here, you can look at this one. This is definitely symmetric to the y-axis right here. So this is an even function. Let's look at this one over here. This one here, if I took this thing and I rotated it 180 degrees, I get the exact same thing. Okay, so this is symmetric to the origin, which means this is an odd function right here. Okay, this one right here, it's not even because it's not symmetric to the y-axis, because otherwise this would be over here and this would be over here, right? Would also be in those places. And if I take this and I try to rotate it, well, now it's below the x-axis. It's not above the x-axis like it was right here. So it's not symmetric to the origin either. So this thing is neither. Okay. Determine if the functions below are even or odd or neither. Okay, so remember I have a couple of rules. I have a rule that says f of negative x equals negative f of x. And then I also have the other rule says f of x is equal to f of negative x. Right? Those are my two rules from right here. F of negative x equals f of x. F of negative x equals negative f of x. So, this rule will tell me this would be an odd function right here, and this would be an even function right here. So here's what I want to do with these. I would always check to see if it's even first, because that's the easiest thing to do. I think it's easier. Okay, so I'm going to find, and I got to find f of negative x in both of these anyway, so I might as well just, what's f of negative x? Well, that's going to be negative x cubed minus negative x. All right, if I take negative x times negative x is positive x squared times negative x is negative x cubed. And then a negative times a negative is a positive. Okay, so this is definitely not equal to that, so this is not even. Okay, so I can eliminate that. Now I'm going to test to see if it's odd. So I'm going to find negative f of x. Now if negative f of x is equal to f of negative x right here, if these two things are equal, then it's going to be odd. If it's not, then it's neither. Okay, so this is going to be negative x cubed minus x, like that. So this would equal negative x cubed plus x. Oh, well, that's equal to this. So since these two are the same, that implies, so we write it implies, it is odd. That's an odd function. Now, it wouldn't hurt you to go to your graph and plug in x cubed minus x and you should always clear that out first, right? X cubed minus x, and reset your window so that you can see all four quadrants, and hit graph, and you look at the graph. So this thing looks a little bit, it looks like this. So yep, that's an odd function. All right, let's look at the next one. So the first thing we'll do is we'll find f of negative x. So we'll plug in, we'll get negative x squared plus 1, which is just x squared plus 1, because the negative times the negative is a positive. Hey, negative f of negative x is equal to f of x. This thing is even. Now I suppose it could be both even and odd. So you should check that. All right, so go ahead and find negative f of x. So that would be negative x squared plus 1, which would be negative x squared minus 1, which is not equal to this, so that's not odd. Okay, let's check this one here. So f, or this, I guess h of negative x would be negative x cubed minus 1, which is going to be negative x cubed minus 1. Well, that's not equal to this, so it's not even. So now we'll find negative h of x. So that just takes, puts a negative on the front of this thing. And that's going to be negative x cubed plus 1. That's not equal to this, so it's not odd either. So this one's neither. Okay. So, here's your assignment. There's a couple pages on here. The writing is it's not very got very good resolution, so I posted the assignments or the pages, nice and clear pictures in Google Classroom. So check that out. Have a great day, guys.